Hello and welcome to this new video where we discuss mathematics and physics on the board. Today what we are going to discuss is basically some mathematics which has to do with geometry, and in particular what people would call pseudo-Euclidean or pseudo-Riemannian geometry. And in this case we are talking about the Minkowskian geometry. In particular, one of the things we are going to be interested in is basically to characterize that geometry via its isometries, and in particular a specific kind of class of isometries that then in a later video we are going to connect with some physics. Okay, so let's look in what context in general Minkowskian geometry actually appears. So usually you consider that you've got two vectors that you call here, for example, u and v, and you say that they belong to a vector space that is R cross Rn. And the reason why this is depicted that way is because in Minkowskian geometry, as you're going to see on the second line, the first coordinate plays a different role as opposed to the other coordinates. And so you need to kind of differentiate this when you talk about the set you're going to act on. At least traditionally, this is done this way. So here you introduce an inner product. So this is this kind of brackets, like this triangular shape. And then I put an M here to signify that this is a Minkowskian metric. Now, the way it reads, by definition, at least if you are in a so-called orthonormal, or normality here being defined slightly differently from before, but at least if you have an orthogonal and then normal with like a minus sign for the 1, 2, and 3 indices, or whatever, 1 to n indices, and then plus 1 for 0, that's basically what normality is going to be about. So the bottom line is that at least in any kind of appropriate basis, you can write basically the inner product between u and v in this particular fashion, okay, where the u naught and v naught are the 0th coordinate corresponding to this r here, and then the n coordinate for the Rn part here range from for an index going from 1 to n. And then here, this is simply the traditional Euclidean metric, again expressed in an orthonormal basis in this Euclidean space. Okay, so that's the traditional thing. So what Minkowskian add to it is really this minus sign, and here this plus for the 0th coordinate in an n plus 1 space. Okay, so basically that's it. Now, what we are going to look at, and that's because basically that's enough to actually characterize fully the isometries of this, is to look at the case where we simply have R cross R. So essentially n is equal to 1 in this particular case, and that's what we are going to look at, because in a short video that's mostly what we can do, and also it captures the entirety of what we need to really look at. So what we imagine is that there is a linear map that we call L, and basically it has these 4 entries that are unknown so far. So it's A, B, C, and D. And what we want is to find all the possible linear maps such that if you actually take the inner product of LU with LV, then it has to be equal to the inner product of U and V in Minkowskian kind of space. And this has to be true for any u and v. So we are going to obtain equations that are for essentially A, B, C, and D instead. Okay, so let's have a look at what that gives. So first of all, let's try to find out what LU is. So if I want to find LU for whatever u is going to be, this is basically A, B, C, D. And then here I've got u naught, u1. And so that's equal to, so A u naught plus B u1. And then here we've got C u naught plus D u1. Okay, so this is my new vector. Likewise, if you do the same for V, this is going to be, like I just need to copy paste really, V naught V1, and that's going to be A V naught plus B V1, and then C V naught plus D V1. Okay, so now let's look at what the inner product of these two guys is going to look like. So if I actually look at LU, LV, so the Minkowskian inner product, then I'm going to get this thing here. But I need to replace all of this instead of U naught and V naught. So I'm going here to get A U naught plus B U1, then times A V naught plus B V1. Okay, so that's this product here, and then minus the other one. So that's C U naught plus D U1, and then C V naught plus D V1. Okay, so that's what we have. And then basically I need to expand and factorize to put these things in a more in an easier way to digest. So first of all, I want to try to put everything that is going to be factorized by U naught, V naught. And if I actually look at this, I'm going here to get A squared U naught V naught. So I'm going to get A squared. And then I'm going to get as well C squared here. So that's minus C squared, and then times U naught V naught. Okay, so that's one thing that I have. Now let's look at what happens if I put minus, and I want to put the term now that is going to be factorized by U1 V1. So here I've got U1 V1, so I've got, and in particular here, I've got U1 V1 with a minus there. So I'm going to get basically D squared minus B squared, and that's U1 V1. And then I need to put what are the terms that are basically missing from there, okay? And what you're going to see is that the cross terms are going to be AB, okay? So there is an AB for U naught V1. So there is plus AB. And then there is also, so AB as U naught V1, and also I've got minus U naught V1, so minus CD. And all of that, it turns out, is U naught V1, but then plus also U1 V naught. Okay, so basically that's the idea. And the reason why this is important to factorize it that way is because this needs to be equal to U naught V naught minus U1 V1. And essentially for any, that's really the crucial part, for any values of U and V in R cross R. And so what that means is that these things here plays a role of, if you will, basis vectors, okay? And what I want is essentially to equate two vectors here, where essentially I need to equate the components. So what I see is that the component associated to the cross terms here has to be 0. What I see is that the component associated to the U naught V naught has to be 1. And so this is only possible if we are going to have, and this is really given by this in particular, this is basically going to be possible only if the following equations are followed. So A squared minus C squared is equal to 1. Then we need to have D squared minus B squared is equal to 1. And then we need to have here AB minus CD is equal to 0. Now the problem is that we've got actually 4 unknown variables, and so far we actually managed to get 3 equations. So for the special class that I'm looking at, of transformations, I'm going to look at one that has the determinant of that stuff that is actually +1. Okay, and so this is going basically to set the score and basically make the thing solvable. So I'm asking that basically AD minus BC, so DA minus BC is equal to +1. So that's now my requirement that I want to satisfy, and this particular equation stands for det of L is equal to +1. Okay, so of course you could try to solve these things, etc., but that's not really my point here. I just want to give you an idea of a very typical solution that can come out of it. Now, the actual form of this equation, a squared minus c squared, essentially let us deduce that a squared minus c squared, let us think that a could be of the form of the cosh of some real number alpha, and you could have as well that c then would be sine of some alpha as well. Okay, now of course, because they are squared, in principle there could be some plus and minus there because it's only with respect to the squared thing. So for now, we simply decide that this is plus for the others, plus for these two guys, and then we're going to see whether we reach any inconsistencies with the other ones. Okay, so we put an ansatz. This ansatz at the very least satisfies the first equation. Here we can also say that we've got this particular equation here, but what we can say rather is on that side, so from AB minus CD equals 0, we have basically that B times cosh alpha, and then minus D sine H alpha must be equal to 0. Now, there are perhaps many possible things that are going to basically do that. But the thing is that, of course, here you've got cosh and you've got hyperbolic sine. These are not the same functions, of course. And so if you want that to be true, whatever the value of alpha is, then essentially you're going to reach the conclusion that basically B must be equal to plus or minus essentially sine H alpha. And then likewise, you need to have D, which is going to be equal to plus or minus cosh alpha. And so what I mean by that is that the plus here, so when B is plus sine H, then D has to be equal to plus cosine H. Okay. So basically that's this particular assumption does actually match this equation. So this equation turns out to be checked if B and D actually satisfy this equation. And what is going to disentangle this thing in terms of whether it should be plus or minus is this final one here. So we need to have A times D minus BC is equal to plus 1. So basically here what we have is that D times S, so here D, we said it was plus cosh, so let's say plus minus cosh squared of alpha, then minus plus or minus sine H squared of alpha is equal to, and it has to be equal to plus 1. And this is only possible if we cross the possibility of the minus sign here being there. So this is not possible. So it's only possible if we choose the plus version of it. Okay. So consequently, what we find, and again, like this particular, this is an identity. If, for example, you don't understand where this identity comes from for the cosh, and so the fact that cosh squared minus sin h squared is equal to plus 1, then this is something we can have a look at if you want. Please let me know in the comment section if this is something you want to look at. But that's a typical equation from hyperbolic kind of trigonometric function. So then in that case, what we have in the end, and I think I can put this in a, well, actually, I will put that probably here as a sort of final summary, is that the thing that works very well is actually something of the form cosh of alpha, then sine h of alpha, sine h of alpha, and then cosh of alpha. Okay, so this is going to be a set of transformations which represent isometries of the Minkowskian geometry, so of the Minkowskian inner product. Now, in the traditional case, of like isometries of the Euclidean metric, then the transformation corresponding to that class, and in fact the determinant being +1, then correspond to rotations. Okay, in that case, what that means is that if you were to have, for example, you apply that transformation onto a vector, then the corresponding map, so parametric map you're going out of it, is going to be a circle. Okay. Now, as it turns out, well, circles are roughly, quite simple to draw, at least to visualize and conceptualize, but that's not quite the case when it comes to cosh and kind of sine h functions and so on. So instead, in principle, here on that side, you should see a visualization of, instead of a circle, what these things looks like. And in fact, that's a branch of an hyperbola. And what happens is that as you increase the value of the parameter, then essentially you're going to see the vector kind of going along this hyperbola, up to, in principle, infinity. And this particular set of vectors, if you apply it on two different vectors, is what is going to give rise to isometries, in the sense that, again, the inner product between these two vectors is going to be preserved by that transformation. Okay, so that's the reason why the Minkowskian geometry is said to be hyperbolic, is because the transformations that actually preserve the inner product turn out to be branches of hyperbola. And so it's an hyperbolic geometry. So that's it. And this has tons of consequences that we'll discuss in later videos as well, in mathematics and in physics as well. Okay, so if you've got any questions or comments on this particular transformation, on maybe some aspects of hyperbolic trigonometry, by all means, do let me know in the comment section. Otherwise, see you in the next video.